Here's the part that should keep you up at night. We've found those planets. We've photographed them, analyzed them, sent machines to crawl across their dead surfaces. And the more we study them, the harder it becomes to look away, because they don't feel alien. They feel familiar. The solar system is not just a neighborhood of planets. It's a museum of warnings. Each world is a display case showing a different way a planet can fail. Through fire, through cold, through chemistry that almost worked, through stability that quietly collapsed. And Earth? Earth is standing in that museum, looking at the exhibits, not yet realizing it might someday become one. This is the countdown of 10 dead worlds, and what they might be trying to tell us. All right, let's go. Number 10. Mercury, the world the sun destroyed. Picture a planet so close to its star that the sun hangs 3 times larger in the sky than it does from Earth. A place where daytime temperatures exceed 800 degrees Fahrenheit, where the ground has been baking without relief for over 4 billion years. No clouds to block the radiation, no thick atmosphere to buffer the heat, just rock, scars, and a relentless cosmic furnace inches away. That's Mercury, and it looks exactly like what happens when a world stays too close to an aging star for too long. NASA's Messenger mission spent years mapping Mercury in detail, and what it found was essentially a planetary skeleton. Ancient impact craters cover the surface like old wounds that never healed. Enormous cliffs called rupes stretch for hundreds of miles, the result of the planet slowly shrinking as its interior cools and contracts. Mercury is a world literally collapsing in on itself, 1 millimeter at a time, over geological eternity. But Mercury's most important lesson isn't the heat, it's the stripping. Any atmosphere Mercury tries to build gets dismantled almost immediately by solar wind, a constant stream of charged particles blasting off the sun's surface. Molecules are knocked loose, carried off into space. The planet is left naked, perpetually exposed, unable to hold on to the thin protective layer that makes complex chemistry and life possible. Think of it like trying to keep a candle lit inside a wind tunnel. The flame isn't the problem, the wind is. Now here's where it gets personal. Earth currently sits in the sun's habitable zone, that narrow band of distance where liquid water can exist. But the sun isn't static, it's getting brighter. Every 100 million years, it outputs slightly more energy. In a few 100 million years, Earth will receive significantly more radiation than it does today. In a billion years, the consequences could cascade into something catastrophic. Mercury isn't just an inhospitable rock. It's a preview, a time-lapse of what proximity to a slowly brightening star does to a world that can't fight back. And the terrifying footnote is this: the sun is only halfway through its life. Whatever Mercury has already suffered, the worst is still ahead. Number 9. Pluto, the frozen graveyard, at the edge of sunlight. When NASA's New Horizons spacecraft flew past Pluto in 2015, scientists expected a dead, featureless ball of ice. What they got instead was a world of shocking complexity. Nitrogen glaciers, towering water ice mountains, layered hazes drifting through a thin atmosphere, and a vast heart-shaped plain so smooth it suggested geological activity far more recent than expected. For a moment, Pluto felt almost alive. Then you remember the temperature, nearly minus 400 degrees Fahrenheit. You remember that sunlight arrives there so weak that high noon on Pluto looks like twilight on Earth. You remember that Pluto's atmosphere literally freezes solid onto the surface during parts of its 248-year orbit, only to partially thaw and return as the planet swings closer to the sun. Pluto is a world on the very edge of energy itself, and that edge is where biology goes to die. Life, as far as we understand it, is fundamentally a story about energy flow. Photosynthesis, metabolism, reproduction, all of it requires a constant current of usable energy moving through a system. Pluto sits so far from that current that the lights are essentially off. It has the ingredients, perhaps. It has the chemistry. But without energy to drive the reactions, nothing moves, nothing grows, nothing begins. Imagine a city where the power grid slowly shuts down, not all at once, but one district at a time. The hospitals go dark. The water treatment plants stop. The grocery stores close. No catastrophe strikes. No disaster occurs. Everything simply freezes in place. That's Pluto. A world where entropy won not through violence, but through deprivation. The warning Pluto offers is subtle, but it cuts both ways. We talk constantly about Earth getting too hot. But planetary history shows that the knife has two edges. Too much energy from a star destroys worlds. Too little energy is equally lethal. The narrow band where life thrives isn't just about distance from the sun, it's about maintaining exactly the right energy balance for billions of years without slipping in either direction. Pluto slipped. Slowly, quietly, completely. Number 8. Titan. A world where the chemistry survived but life didn't. If you could somehow observe Titan from high above without knowing anything about it, you would almost certainly conclude you were looking at a living world. Rivers carve valleys through its surface. Rain falls from orange clouds. Lakes shimmer near the poles. Seasons cycle across a globe wrapped in an atmosphere thicker than Earth's. Everything about Titan's behavior screams habitability. But look closer. The rivers aren't water. They're liquid methane. The rain is ethane. The lakes are hydrocarbon seas cold enough to freeze any Earth-based biology solid. Saturn's largest moon, explored in extraordinary detail by the Cassini spacecraft and the ESA Huygens probe, is a world where organic chemistry runs wild. Molecules combining, breaking apart, drifting through the atmosphere, settling on the surface, endlessly, for billions of years. And yet, no confirmed life. That's what makes Titan one of the most philosophically unsettling places in the solar system. It proves, in the most vivid possible way, that having the ingredients isn't enough. The recipe can sit on the counter forever and never produce a meal. Complex organic molecules exist on Titan in staggering quantities, some of the same building blocks found in every living cell on Earth. The chemistry is there, the complexity is there, the result isn't. It's like a library that contains every book ever written about a subject, but the subject itself has never been discovered. All the knowledge, none of the knowing. For scientists studying life's origins, Titan is invaluable, precisely because it shows us a system running the prebiotic chemistry experiment at planetary scale, in real time. For the rest of us, it raises a question that doesn't have a comfortable answer. If Titan, with all its richness, all its organic complexity, all its atmospheric activity, never crossed the threshold into biology, how rare is the spark that actually starts life? How many Titans are out there, running the experiment perfectly, for billions of years, producing nothing? And if that spark is truly rare, then Earth's existence isn't just lucky, it's almost statistically impossible. Number 7. Europa. The ocean that never saw the sky. Beneath Europa's cracked and frozen shell lies an ocean. Not a lake, an ocean. Larger than all of Earth's combined. Liquid, ancient, and hidden under miles of ice that may be several times the height of Mount Everest. NASA's Galileo mission found strong evidence for this buried sea decades ago. The upcoming Europa Clipper mission is designed to investigate it in unprecedented detail. From a purely scientific standpoint, Europa is one of the most exciting objects in the solar system, a place where liquid water, chemical energy from hydrothermal activity, and basic organic compounds may have coexisted for billions of years. From an existential standpoint, Europa is haunting, because if life exists there, it has never seen the sky. Whatever swims or drifts or metabolizes in that dark ocean has no concept of Jupiter hanging massive overhead, its storm bands swirling in colors of rust and cream. It has no concept of the sun, a faint dot 400 million miles away. It doesn't know that stars exist. It has no horizon, no open water, no seasons driven by a warming sky. Just darkness, pressure, chemical gradients, and the faint heat of hydrothermal vents below. There is a type of prison that has no bars. The walls are too thick to see, too cold to melt, too vast to comprehend. Europa may be filled with life living in exactly that kind of prison, capable of existing, perhaps even thriving, but permanently sealed from the universe beyond. And this raises a question that reframes the Fermi paradox entirely. We look at a silent universe and wonder, where is everyone? Maybe the answer isn't that life is rare. Maybe the answer is that countless worlds like Europa are full of life, microbial, complex, perhaps even intelligent, but locked under ice so thick that no signal ever escapes, no rocket ever launches, no civilization ever reaches the stars. In that scenario, the universe isn't empty. It's full of prisoners. Number 6. Io. The moon that never stops dying. Io looks, at first glance, like someone spilled an artist's palette across a moon. Yellows, oranges, deep reds, patches of black, It's one of the most visually striking objects ever photographed in the solar system. Those colors are sulfur, and they are the signature of a world in constant, violent self-destruction. Io is Jupiter's innermost large moon, and it holds a record no world would want, the most volcanically active body known to science. Hundreds of volcanoes erupt continuously across its surface. Some launch plumes of material hundreds of miles into space, towering columns of sulfur dioxide that freeze and fall back as yellowish snow. Lava flows constantly reshape the terrain, burying craters as fast as they form, making Io one of the youngest surfaced worlds in the solar system despite being billions of years old. The culprit is Jupiter's gravity. As Io orbits, it's simultaneously tugged by Jupiter and nudged by neighboring moons Europa and Ganymede, locked in a gravitational resonance that prevents it from settling into a circular orbit. The result is constant tidal flexing, Io's entire body stretching and compressing on every orbit, generating enormous heat through friction. The moon is being kneaded like dough by gravitational forces it cannot escape. Think of a stress ball squeezed and released a billion times a second. Eventually, the heat generated isn't metaphorical, it's geological. Io's lesson isn't about climate change or atmospheric chemistry. It's about something more fundamental, the illusion of geological stability. Standing on Earth, you feel permanence. Mountains seem eternal. Continents seem fixed. The ground beneath your feet seems like the most reliable thing in existence. Io is a reminder that planets are dynamic systems held in temporary balance by forces we rarely think about. Shift the gravitational geometry, and paradise becomes an inferno. The line between a stable, habitable world and a volcanic hellscape isn't drawn in stone. It's drawn in the invisible math of orbital mechanics, and it can be redrawn. Number 5. Mars, the planet that lost everything. Mars didn't start as a corpse. That's the most important thing to understand about it. The evidence gathered by decades of NASA missions, from the twin rovers Spirit and Opportunity, to the long-running Curiosity, to the newest addition, Perseverance, tells a story that's difficult to fully absorb. Ancient river valleys cut through Martian highlands. Dry lake beds spread across crater floors. Sedimentary rock layers, formed only in the presence of standing water, sit preserved in cliffs and canyon walls. Mineral deposits that form specifically through prolonged water interaction are scattered across the surface. Billions of years ago, Mars was wet. Perhaps not tropical, perhaps not teeming, but wet, with a thicker atmosphere, a warmer climate, and the basic conditions that, on Earth, eventually led to life. Then something broke. Mars lost its global magnetic field. Scientists believe this happened relatively early in its history, possibly as the planet's core cooled and its internal dynamo shut down. Without that magnetic shield, the solar wind had a clear path. Over hundreds of millions of years, it slowly stripped away the Martian atmosphere, molecule by molecule, particle by particle. As atmospheric pressure dropped, temperatures plummeted. Liquid water became unstable at the surface. The rivers dried. The lakes evaporated. The sky thinned to a whisper. Today, Mars is essentially a geological crime scene. The evidence of a different world is everywhere, frozen into the rock, written in the chemistry of ancient soil. But the civilization that might have existed, the biology that might have taken hold, the planet that might have mattered, gone. Walking the Martian surface, you would find the ruins of an environment. Not ruins of cities or structures. There's no evidence of that, at least not yet. But ruins of conditions. The infrastructure of habitability, preserved in stone, like the foundation of a house whose walls were removed and whose roof blew away eons ago. Mars is not a warning about what's coming. It's a warning about how quietly it can happen. No asteroid, no explosion. Just a magnetic field slowly dying, and a thin sky disappearing into space, and a world becoming uninhabitable so gradually that nothing alive long enough to notice it would have had time to act. Number 4. Rogue planets, worlds exiled from the light. Most planets have stars. That simple fact, so obvious it barely registers, turns out to be one of the most important conditions for a habitable world. But scattered through the galaxy are worlds that don't. Rogue planets, free-floating planetary bodies untethered to any star, drift through interstellar space in complete darkness. Some were almost certainly ejected from their home systems during gravitational interactions early in those systems' histories. Others may have formed directly in the voids between stars, never knowing a parent sun at all. Either way, they are out there, planet-sized objects, perhaps billions of them across the Milky Way, moving silently through permanent night. No sunrise, no seasonal warmth, no photosynthesis, no solar energy to drive the complex chemistry that life, as we understand it, requires. Imagine Earth suddenly ejected from the solar system. Not destroyed, just thrown out, sent drifting into the void at high velocity. The first changes would be invisible. The solar energy hitting the surface would diminish day by day. Within a year, global temperatures would plunge catastrophically. Surface water would freeze. Most complex ecosystems would collapse within decades. The atmosphere itself would begin to freeze out over thousands of years, settling onto the surface as snow. Some researchers have speculated that certain rogue worlds might maintain subsurface liquid water for billions of years, heated by residual internal warmth or radioactive decay, and with it, the faint possibility of microbial life in deep aquifers. But any civilization, any complex biosphere dependent on sunlight, would not survive the exile. What makes rogue planets disturbing isn't their existence in deep space. It's what they reveal about the assumption we never examine, that our orbit is permanent, that the sun will rise tomorrow. On human timescales, that assumption is reasonable. On cosmic timescales, in a galaxy churning with gravitational interactions, stellar passages, and ancient disruptions, that assumption is a gamble we've been winning for 4 billion years. Some worlds lose that gamble. They're still out there, falling through the dark, carrying the cold memory of a sun they no longer have. Number 3. The ghosts of planets around white dwarfs. Every star dies, ours included. When astronomers turned their best instruments toward white dwarfs, the dense, cooling remnants left after sun-like stars exhaust their fuel. They expected to find lonely stellar corpses slowly fading in the dark. Instead, they found something that looked, uncomfortably, like evidence of a crime. Many white dwarfs are polluted. Their atmospheres, which should contain only the lightest elements, hydrogen and helium, instead show calcium, magnesium, iron, silicon. Elements that have no business being there unless they arrived from somewhere else. The culprit, identified through decades of observation using instruments like the Hubble Space Telescope and the Keck Observatory, is planetary debris. These white dwarfs are consuming the shattered remains of their own planetary systems. Rocks, moons, and perhaps entire planets torn apart by tidal forces or destabilized by the star's evolution, ground into rubble and slowly spiraling inward to be devoured. These are stellar graveyards. And they're common. The chain of events that creates them is grimly predictable. When a star like our Sun reaches the end of its main sequence life, it expands into a red giant, ballooning outward hundreds of times its original size. Inner planets may be engulfed entirely. Outer planets are gravitationally destabilized as the star sheds mass. The once ordered architecture of the planetary system, billions of years in the making, collapses into chaos in cosmological seconds. What survives gets pulled apart. Here's the part that should feel uncomfortably personal. Our sun will go through this process. In roughly 5 billion years, it will expand, transform, and eventually collapse into a white dwarf. Earth may be engulfed by the expanding solar envelope. If not, it will be scorched beyond recognition, its oceans long gone, its atmosphere stripped away, its surface reprocessed into something unrecognizable. And then, perhaps, its fragments will spiral slowly into the cooling sun. One more polluted white dwarf in a galaxy full of them. One more signature for any civilization evolved enough to read it, that something was here. Somewhere among those distant stellar graveyards, there may already be the signatures of planets that once hosted life. Worlds that had their own blue skies, their own weather, their own billions of years of complex chemistry, now reduced to trace elements in a dying star's atmosphere. Evidence of existence, preserved in the very thing that erased it. Number 2. Venus, the planet that lost control. Venus should have been us. That's the quiet horror at the center of its story. By almost every structural measure, Venus and Earth are twins, nearly identical size, nearly identical mass, formed in the same region of the early solar system, from the same pool of material, at roughly the same time. For a period in the solar system's early history, some climate models suggest Venus may have had liquid water on its surface, perhaps even shallow oceans, perhaps even conditions that, given enough time, could have supported life. Today, Venus is the most hostile surface in the inner solar system. Its atmosphere is 96% carbon dioxide, creating a pressure at ground level more than 90 times that of Earth's, equivalent to being nearly a mile underwater. Surface temperatures average around 867 degrees Fahrenheit, hot enough to melt lead, hot enough that the planet glows in the infrared. Clouds of sulfuric acid envelop the entire globe, creating a permanent reflective shroud that, paradoxically, bounces away a significant portion of incoming sunlight while trapping the rest with brutal efficiency. No spacecraft built by humanity has survived on the Venusian surface for more than a couple of hours. What happened to Venus appears to have been a runaway greenhouse effect, a feedback loop so thorough and so self-reinforcing that it erased an entire world's habitability. As the planet warmed, water vapor, itself a greenhouse gas, entered the atmosphere in increasing quantities. That water vapor trapped more heat. Higher temperatures drove more evaporation. The cycle fed itself, accelerating until the oceans were gone. The water vapor dissociated in the upper atmosphere, the hydrogen escaped to space, and what remained was a permanent, suffocating CO2 blanket with no mechanism for removal. The thermostat didn't just break, it melted. Climate scientists are careful to note that Earth and Venus are not identical, and that a Venusian-style runaway isn't considered an imminent risk for our planet under current models. But the word imminent is doing a lot of work in that sentence. Venus demonstrates with absolute clarity that planetary climate systems contain thresholds, points past which feedback loops take over, and the system accelerates toward a new equilibrium that nothing biological can survive. The terrifying implication isn't that Earth will inevitably become Venus. It's that Venus may have been similar to Earth, and the difference between the two outcomes may have been smaller than we're comfortable admitting. A different orbital resonance, a slightly earlier loss of water, a feedback loop that started 1 billion years earlier. We didn't choose to be Earth instead of Venus. We were born here, in this orbit, at this distance, at this moment in the Sun's life. The planet next door is a reminder of what happens when the variables don't align. It isn't a different story. It's the same story, with a different ending. Number 1. Earth after the Sun begins to die. Everything in this video has been leading here. Not to another planet, not to a distant moon or a frozen dwarf world at the edge of the solar system. Here, the most terrifying dead world that might be warning us about Earth's future is Earth itself. The Sun is approximately 4.6 billion years old, right around the midpoint of its hydrogen-burning main sequence life. Right now, today, it is stable, consistent, generous. It rises every morning and drives the photosynthesis, the weather, the ocean currents, the entire cascade of energy that makes this planet's extraordinary complexity possible. But stars change. Ours is already slowly brightening, a natural consequence of nuclear fusion gradually converting hydrogen to helium in its core, causing subtle changes in internal structure over geological time. Models of solar evolution indicate that Earth's surface temperature will begin increasing meaningfully over the next several 100 million years. In roughly 1 billion years, the increased solar output may push Earth's climate past the threshold where the oceans can be maintained. This isn't a political statement, it isn't a projection. It's orbital mechanics and stellar physics, as certain as the math that predicted Neptune's position before anyone pointed a telescope there. Long before the Sun becomes a red giant, Earth may already be unrecognizable. The oceans evaporate, water vapor floods the upper atmosphere, ultraviolet radiation breaks water molecules apart, hydrogen escapes to space. Without oceans, the carbon cycle breaks down. CO2 accumulates. The surface temperature climbs toward Venusian levels. Complex multicellular life becomes impossible. Then simple life. Then perhaps life itself. Then comes the final chapter. In approximately 5 billion years, the Sun exhausts the hydrogen in its core. Shell burning begins. The outer layers expand, slowly at first, then dramatically, transforming the Sun into a red giant star that may extend to or beyond Earth's current orbit. Whether Earth is physically engulfed or simply incinerated at close range, the outcome is the same. The oceans are long gone. The atmosphere has long since been lost. The surface, whatever remains of it, may be melted and resolidified multiple times over. Every mountain range humans have named, every ocean current we've charted, every forest, every city, every grave, every monument. Gone, not in an explosion, not in an instant, but in a slow, physics-driven inevitability that began the moment our solar system formed. Compress all of human history into a single book. Every civilization, every language, every war, every breakthrough, every work of art ever created. Place that book beside the lifespan of the sun. Human history would occupy a few lines on one page of a volume thousands of pages long. That is the scale of what we're embedded in. Mercury warned us about stellar heat. Pluto warned us about the cold edge of energy. Titan warned us that chemistry isn't enough. Europa warned us that life can be imprisoned. Io warned us that stability is borrowed. Mars warned us that habitable worlds can die quietly. Venus warned us that feedback loops can be irreversible. Rogue planets warned us that orbits aren't permanent. White dwarf systems warned us what remains after the end. Earth will experience versions of most of these stories before it's finished. The most disturbing conclusion planetary science keeps arriving at isn't that Earth is in immediate danger. It's something more fundamental. Planetary death isn't the exception, it's the rule. Every world has an expiration date. Every ocean eventually disappears. Every atmosphere transforms. Every star ends. The universe follows its laws with perfect, indifferent consistency, and those laws have already turned the cosmos into a graveyard of worlds that once had possibilities. What makes Earth extraordinary isn't that it exists. It's that everything required for its existence has held together, in exactly the right configuration, for long enough to produce this moment. You, watching this, capable of understanding the scale of what surrounds you. A stable star, liquid water, a magnetic field, an atmosphere, the right distance, the right chemistry, the right sequence of ancient accidents. Remove enough of those, and Earth starts to look like every other dead world in this video. The universe doesn't owe us continuation. It doesn't protect civilizations. It doesn't make exceptions. It simply runs its equations. And so far, ours have come out in our favor. So far, if these worlds are warnings, the message isn't you're doomed. The message is simpler, and in some ways more profound. You are temporary, and temporary things are worth protecting. Sleep well. I'll be sharing more similar videos in the future, so subscribe to stay tuned.